Yeah, a little hello from my side. Whoever is not seated yet, maybe grab a seat. Maybe I first introduce myself. My name is MATHIAS WIESE. I'm the CEO at ADDDAM. And yeah, that's actually the reason why we meet up here today. We want to present ourselves to you, emerge from stealth in theory. And we are entering the business of aluminum additive manufacturing right now. We see a lot of conversion going on concerning different technologies that are advantageous. And yeah, that's the reason why we meet up here again. So a happy day to you. We welcome here at the Durst campus, and also be welcome in the online stream, whoever is listening right now. And yeah, I just don't want to waste too many words on our mission right now, because in the end we will wrap it up. We will have some of our customers here to report what their vision on AAM is, and we have some of our enablers here today, our suppliers, who will give you some insights on how additive is evolving and coming together. And in the very end I will wrap it up. But for now I would give the words to HARALD OBERRAUCH, the president of the Technikon Group, and give an impression about what the mission, or where the mission came from that ADDAM is on, and how this complete idea came together. HARALD, it's your stage.
Thank you, Matthias, very much. Welcome to everyone. Welcome to Durst. Welcome to the Kraftwerk. I'm HARALD OBERRAUCH, the owner of Technikon. Technikon is a family-owned holding where we have few participation. The main companies are Durst. You're sitting here in the facility, in the production facility. We have another facility in Linz. The other company, it was founded in 1936. I'm the third generation now. I don't know, there is a legend and a myth about the third generation. I'm happy I have another company, you know. The first one built it up, or found it, the second one built it up, and the third one make the bankruptcy. I hope to not do this, but fortunately I have another company. It's called Alupress. Sorry, with Durst we make digital printing systems for different markets. The other company is it's called Alupress. It was founded in around 68. I'm in the second generation, so I'm lucky. There we are. It's a tier 1 company for the automotive market, where we build components with the technology of die casting. And there is another little flower growing up. It's Imagina Biotechnology, where we do diagnostic for skin cancer. Few years ago, it was the period of the COVID, and it's a nice story. We founded the Kraftwerk over there. You will go there. But the story is that a little student came to me, or a young student of Durst came to me and told me, "How do you know what you have in your hands? We have UV lamps." They said, "Yeah, okay, no, we use them to dry the inks, no, for when you print, and the drops are going down. You need these lamps to dry them." And he told me, "You can kill the COVID virus with this." We called it Habitat. That's the main product, or the first product what came from the employees, no. We built it up in about 10 weeks with the team calls, and sometimes we meet up over here. But why I would like to tell this to you? We said, come on, that's ideas of our employees, of our people, of our family. Why don't do this in a structured way? And so we built up the Kraftwerk. Then Stefan Waldner came to us and said, come on, you have a print head in your hands. I think I can build a 3D printer around of it. We showed the first prototype of this printer, where we do technical ceramics. That's a really curious and really important material, and we show it up the first prototype at the Form Next. You will see it over the Kraftwerk. Another company, Durst Media Company. You see these guys over here. They are filming. They make communication. Simon was the head of communication of Durst, and he was so good with his team that we said, come on, you have to go out into the market and offer your service even to third parties. What we did, spin off again and go to the Kraftwerk. Then, last but not least, obviously ADDAM. ADDAM, I don't know if someone knows what ADDAM means. ADDAM is A for Alupress, D for Durst, the 3 Ds for 3D printing, and AM, additive manufacturing. That's a little bit different story. 7-8 years ago, we bought the EOS 3D printer mainly for producing channels, cooling channels for the die casting tools. That was the main business. We were a little bit early, I think, 7-8 years ago. And during the COVID, we said, now it's the time. After the COVID, I'm convinced that you can sell really components in series to the customers. And therefore, we did another spin-off. We bought the old printing machine. We get a new printing machine today. And that's why we are here today. And that's why we would like to prove you that 3D is not the future. 3D printing is already today. Thank you very much.
Thanks, Harald, for the announcement. So I guess it's now our part to convince.
That's your job now. Thank you.
Yeah, what is more convincing than some voices from customers? So I'm really glad that Francesco ARCIDIACONO from Schaeffler Group is joining us today with an expert talk, as well as CARMEN SCHÄFER from Alupress. Yeah, CARMEN, come over here. You start anyway. I will announce a few other people while you're running your presentation up. And yeah, this is the customer's perspective, obviously, but we also want to give an insight into the enabler's perspective. So there's a lot of technology evolvement going on in the 3D printing market. There's also not only hardware going on, but also in the software domain. So I'm really happy to welcome STEFAN HOCHLEITNER here from Materia Fair, talking about tailored materials. I'm happy to have Martina RICCIO here from Additive Industries talking about automated metal printing. And last but not least, BREMER from VCT talking about adaptive machining. Yeah, I don't want to take your stage, so Carmen, please.
Let's try if it works. Do you hear me?
I should switch it on, I guess. Give me a second. There we go.
Okay, I hope, I can hear it. Okay, thank you very much for the introduction, Matthias, and thank you for the possibility to present Alupress today. So my name is Carmen SCHÄFER. I'm head of strategic development of the Alupress Group. Alupress is, as Harald said, an automotive die-cast manufacturer for the automotive industry. And I have the possibility today to show you how AM components can help us in the life cycle of automotive die-cast components. So short motivation. Afterwards, I show the automotive die-cast component cycle. Then 2 examples, prototyping and tooling, and closing with a summary. Okay, on the right-hand side, you can see the huge difference. In case of die casting, we start from the melt. We have the cold chamber die casting process, and on the right-hand side, the prototyping, which starts with the same material in a different condition, from particles with selective laser melting. So we use the AM specifics. We can use high complex workpieces, design geometries, produce small series, and we can support also tooling. So in general, there are 2 approaches for AM. There is the independent standalone version of additive manufacturing with a dedicated design. Or we use it as a complementing technology to traditional manufacturing processes, as in this case, for die casting. So I would like to show you at the beginning the core process chain die casting. So we start usually from the drawing. This is a customer coming with a drawing, and we do a design of the part, supported by simulation, solidification, and filling simulations. And then we go into the tool. We design the tool, and the next step is, and that takes a huge stretch of time, about 12 weeks, to build the die casting tool. And then we go into series production. So how can additive manufacturing help us now? I put you here a graph Number of components is a logarithmic scale and the whole life cycle of a cast component. So on the left-hand side, we have in-house developments. There is no customer inquiry yet, and we can use additive manufacturing here already for the pre-development. Then we have this green stage, introduction. That is the customer request is here. You hear me? The customer request is here. We start with A, B samples. And I come back to the PPAP before starting in series. I come back to that later. On the top you see an actuator housing. This is the full component. And you see the die casting or additive manufactured part on the bottom. As soon as we enter this blue stage, growth and maturity of the component with hundreds of thousands of components, AM can support us, as Harald said, with tooling, to improve the tooling. And afterwards, there is a decline after a few years, and we have the topic of aftermarket. And that is another possibility. You see the die casting and additive manufactured components with higher numbers, usually 500 to 5,000 pieces per year. There are two factors that are important. First is the time to the first prototype. And you see there is high pressure die casting. This reddish area is these 12 weeks, a long time. And we have the possibility to use CNC machining or even better additive manufacturing. So this is the shortest time we can get. And since this tool that I mentioned at the beginning costs quite a lot of money, we have a very late break-even point in numbers. That means also at the early stage, we can use additive manufacturing as a cost-efficient solution for our parts. I have some examples for you. We are now here in this cycle at the very beginning. This is the pre-development stage, not related to customer, in-house developments. So here we have the possibilities, an example of a topology optimization of a DC-DC converter to improve the thermal management. We have the original die-cast design on the left-hand side, and if I want to test this in reality on the test bench, what can I do? I cannot build a tool, there is no budget for this at this stage, and I need it fast and lots of varieties. And then I can use additive manufacturing, and I can get my results. Before I come to the next part, for series production, there is one issue to discuss about AM and die casting. You see it on the first slide, it's the microstructure. High pressure die casting is a fast solidification rate, but AM is even a factor 100 faster. Very fine microstructures, and they result in excellent properties. You have the high pressure die cast, and you have on the left hand side the AM properties. They are anisotropic, you need to consider that. It's not a showstopper, but you need to keep it in mind. And you can see it here on the right hand side, for example, for the thermal conductivity. Also this, if you need to preheat your building stage, or you want to change the thermal conductivity on purpose, you need to consider the building direction in AM. On the right-hand side, we have also the issue of roughness or material condition if you go in a long-term testing. This works fine, it agrees very well, and you need to consider this. So if I come now to the main prototyping process, we want to go in die casting to the PPAP, to the production part approval process. And we have various stages of samples. We have A samples, B samples, C samples, D samples. And you see the blue coloring shows us that we can use A samples already in die casting, in additive manufacturing, and some of the B samples. Small numbers, short time. And on the right-hand side, you see already the agreement as cast 3D printed. And you see mostly it looks pretty good. Some things you need to consider, and in some cases it looks even better. This has to be discussed with our customers. When we go now to the maturity of the component, we have AM supporting our series production. The tool usually has lots of load in terms of thermal cycles. Very high temperature, high load, so you can improve the tool locally by cooling, but also you can improve the tool for the properties. And this is a truck housing, an air dryer. You see the seats for pneumatic ventiles on the bottom. So you see where this red arrow points. And here in the simulation, we have this reddish area. That means I have a macroscopic shrinkage later. I have a hole in the material, which I don't want to have. And you see here, where this greenish area is, we optimized actually this die with an insert with near net shape cooling, and we could reduce this area, improve the material. So this is also how we use AM since 2018, since several years in production. And these are two examples with which we can actually show that AM is already established and can provide us huge help. So we have a cost-efficient and fast production. We have the possibility of tool-free production, individual designs, many modifications, and you see here a step with the potentials for AM. We are using the first two steps. And there is even a much higher potential if we use AM process dedicated with a design. So closing with this, the challenges are still, of course, in the scalability, and I think there will be several talks today going more into depth with this topic. Thank you very much, and I'm happy to answer your question in the Q&A section.
Yeah, Carmen, thanks for the very nice presentation. Just to announce something, we do a dedicated Q&A session after all the presentations with all the experts here in the panel. Obviously, the people following us in the stream don't have the opportunity to ask questions directly, but I invite you to note them down and send them to us via email directly, and we are happy to get you in touch with the experts. So next up, we change the perspective from the Tier 1 to the OEM. So I'm happy to provide the stage to Francesco from Schaeffler to provide us with Schaeffler's vision for AM. And maybe you already got from Carmen's presentation from which domain we as ADDAM are coming and what material we are specifically working on here. So Francesco, tell us your story from the OEM perspective.
Thank you. Good morning to all of you. Matthias, thanks for the introduction. It's really a pleasure for me to be here with you all. I'm Francesco ARCIDIACONO, and in Schaeffler I take care of innovation, but more about that one in a moment. Today I would like to present you the preliminary results and the evidence that we at Schaeffler have after conducting an ongoing project with the partnership of ADDAM during the last few months. But before going into detail, let me spend a few words about Schaeffler, who we are and what we do. Well, with over 84,000 employees worldwide, 200 locations, and a turnover of nearly 16 billion euros per year, Schaeffler is one of the largest family-owned companies, and innovation is embedded in our DNA, as proven by the over 1,200 patents that we registered in 2022. We have three main areas of business: automotive technologies, more about that one in a moment. Then automotive aftermarket, where we provide solutions for repair shops, and our industrial business. Well, there we are somehow among the main producers of bearings for industrial applications. The automotive technologies division is our backbone, and we are responsible for nearly 60% of the total sales of Schaeffler, for a total turnover which is of nearly 10 billion euros per year. What do we do within the automotive technologies division? Well, our goal is to provide with our customers with groundbreaking solutions for highly efficient combustion engines, but also we offer e-motors, e-axles, and then solutions that include the use of fuel cells. And within this complex organization, which is our automotive technologies division, I work in the purchasing department, where we are responsible for managing nearly 1,900 suppliers, which deliver us 26,000 parts, different parts, for a total purchasing volume of 4.5 billion euros annually. In other words, the perfect playground to explore the use of additive manufacturing. Well, additive for us at Schaeffler is not something new. We established an internal additive manufacturing department in 2015. The department is still existing, and my colleague Carsten Merklein is the head of the internal additive manufacturing department. As of today, nearly every Schaeffler plant uses additive. We have internal printers to produce prototypes, tools, fixtures, or material that in general is used within serial production. But to be honest with you, as of today, we do not actively purchase any part from our suppliers which is produced with additive. And some months ago, we decided to start questioning ourselves, and we asked ourselves, how can we include additive manufacturing in a sensible way within the product life cycle, within the life cycle of our products? Well, you know, already Carmen hinted at it before. For sure, we see potential in the development phase of our products. Additive manufacturing for quick prototype is, however, no big news, as Matthias will say. It's an established use case. Where do we see more potential is in the aftermarket phase. So on the right side of the tail of our product life cycle curve. Why aftermarket? Because there additive manufacturing could pave the way for what we call tooling-free manufacturing. What are the characteristics that, in our view, make the aftermarket phase especially appealing for additive manufacturing? Well, two main characteristics. First, the low volumes. You know, we as automotive companies need to then produce after the serial production run for a certain number of years. We have to still produce our products for the so-called aftermarket. In this instance, typically volumes are really low. Typically, it's really infrequent to see that we produce for aftermarket parts with a volume which exceeds the 1,000 pieces per year, but to be honest, in most of the cases, we need to produce just 100, 200 pieces per year. First point. Second point that makes aftermarket especially appealing for additive manufacturing concerns toolings in general, which are worn out after the serial production run. And as Carmen already hinted, replacing a tool is an expensive proposition, and sometimes it's really difficult for us to justify this sort of investments when we are looking, on the other end, to such low volumes. In this sense, a technology like additive could really be a game changer, as it could enable tooling-free manufacturing. To bring our vision closer and closer to reality, we partnered up some months ago with Additive. We somehow decided to focus on one of our commodities, which are, of course, aluminum die-casted components. And so, as we followed somehow a two-step approach together with Matthias and his team. In the first phase, we decided that the best option was to start narrowing the field and highlight and select components that have a high potential for production with additive manufacturing. We started with a list of 436 components, and here the ADDAM team acted as our funnel, so to say. So we narrowed down the field, and we come up with a list of just 8 part numbers that, in our view, are the most promising ones. Why promising? Because volumes are typically very low. Yes, below 150 pieces per year, but we have also some part numbers for which the demands are just in the range of 40, 30, 50 pieces per year. So really not appealing for traditional die-casting manufacturing. And we also had a look at the geometries. Typically, geometries here are not especially complex, and they are also well finishable parts. Then, as a second step, we are also looking at cost, of course. But we are doing so looking at the so-called total cost. What do I mean? Well, for traditional aluminum die-casting manufacturing, the total cost is the sum of the unit production cost plus the tooling cost. In the case of additive manufacturing, the tooling cost is not really there. We have to look at the unit cost, which is, let's be honest here, way higher than the unit production cost for typical traditional aluminum die-casting. One of the outcomes of our project is that the unit cost for additive is 10, 15 times higher, but we do not have the tooling cost. And so in the end, the cost comparison starts to make sense, and the numbers are really, really close one to each other, with an added benefit, though, for additive, which is the absence of stock. Because then you can produce the parts when you need them, and that's extremely appealing for us as a manufacturer. So the cost comparison is ongoing. I'm expecting that in the next weeks we can complete it, and I'm positive also that in the next months we at Schaeffler are going to have the first parts produced with additive manufacturing out of this project. But then what's next? What's the next step? Well, let me present you somehow this vision that we developed together with Florian Schupp, who is the CPO at Schaeffler, and Eric Hoch. Well, the combined use of flexible production technologies such as 3D printers, but also flexible automation, could pave the way for what we have named pop-up cubes, pop-up factories. So our suppliers could somehow package their production equipment within cubes, within containers, and then these containers could travel along the globe to be extremely close to our production facilities with two main benefits. First, the enhanced interaction between supplier and customer, and second, enhanced resilience of the supply chain. And we all know how that is becoming more and more in focus given the latest development. That's our long-term vision, and I'm positive that thanks to ADDAM and projects like the one we are conducting with ADDAM, we will reach it in the next years. Thanks.
Yeah, Francesco. Thanks for the very valuable insights from the OEM perspective. So we got now two perspectives, Tier 1, OEM, two different visions, a bit more development-oriented, more aftermarket-oriented. And we still have a lot of homework to do. And this homework starts in the material domain. So with that said, we shift from the customer's perspective to the enabler's perspective, kicked off by Stefan Hochleitner, who's Managing Director at Materia, who will give you some insights on a new approach to develop materials for AM and maybe some short blinks into what we are doing with them. It's your stage.
Can you hear me? Yeah. Well, thank you, Matthias, for the introduction. My name is Stefan Hochleitner, and I'm the Managing Director of Materia, and I also co-founded the company. So where do we come from? Where did it all start? As things go, it all started out with some problems, some difficulties we had during our research time at the University of Innsbruck. We found that we wanted to use a special material for laser beam powder bed fusion, but the material that we wanted to use was not available yet. So we found that the material number is still a limiting factor to the production. Also, the manufacturing process itself is highly complex, and you can't use let's say steel parameters for the production of aluminum alloys and so on. And it's also strongly dependent on the powder quality itself. And last but not least, the third topic for us was the missing material cycle. We found no good solution to dispose of production waste, and internal powder recycling is only possible to a limited extent right now. So we are working on 3 solutions right now, or working with 3 solutions right now. First of all, we specialize in material engineering. We got the equipment and the knowledge to produce individual materials to your specification and do iterative development using small powder quantities that we can produce in-house. Second of all, as I mentioned before, the process is also a big part of the part quality later on. So we develop also the processing parameters for our developed materials and can do application-specific optimization. And last but not least, we're working right now on a material ecosystem where it's possible to support the entire material cycle for additive manufacturing and recycle as much waste as possible in the future. So what's the first and biggest enabler for our works. It's the powder production itself. We focused on getting machines that can help us with individualized materials, and therefore we use a small batched production machine which uses an inert atomizing process. We use therefore an inductively heated graphite crucible, so it's possible for us to alloy directly in the system. And the outcome of the machine is very spherical satellite-free powder with a D50 particle size distribution from let's say 40 to 150 micrometers, depending on the customer's needs. With the powder production sorted, we focused on material engineering. The process itself, or the materials itself for additive manufacturing, are special in a kind of way that you can tune them to your demands. You can tailor material properties to your needs. You got an influence on strength, hardness, elasticity, and also thermal and electrical conductivity. And it's also possible to fine-tune process-specific powder properties, like the particle size distribution. You got some influence there with production. And it's also possible to account for the influence of volatile components during the process. So if you use a zinc-rich alloy during your laser beam production phase, it's possible that some parts of zinc evaporate and your alloy is not in spec anymore after the process. We can account for this in beforehand, and then after the process you get your alloy in spec. With this methods, we were able to adapt a conventional material for AM here at ADDAM. They are using a die-cast aluminum for AM, or will use a die-cast aluminum for AM, and it was possible with this way for us to enable them to do so. Our material portfolio right now reaches from aluminum alloys, as I told before. Also copper alloys are possible, and in the future we want to get others as well in the company. Right now we have to rely on partners for these alloys, but it's also possible. As I mentioned before, the process is as essential as the material itself, because you got a very strong influence on the part quality with the processing parameters. Depending on laser speed, laser power, and the head spacing, for some examples, you can influence the porosity, surface roughness, mechanical properties, and also the process productivity itself. So it's possible in the future to build bespoke part features and build strategies depending on how your part should perform. You could print your bulk volume of the part with a completely different parameter that has a focus on productiveness, and you can print high strength points in the material with, let's say, a strength parameter, which is slower but enables a greater strain resistance of the parts. So with all these produced parts, there is a lot of waste, and right now, it's not a chain, it's not a cycle, it's a chain where we see. At the top you can see the primary raw material comes in, is atomized by us, is then sieved to the specification of the customer, then transported and processed there. Process, I mean printed. And on one hand you get the part, on the other hand you get the production waste, and there is no good way to dispose of it. And we want to establish a system where you can recycle the production waste and powder scrap. We get them back from you via a deposit system, analyze and treat it in a way that we can use it as an efficient secondary raw material source for the atomization process again. the whole cycle will be using a mass balancing approach to keep track of the powder, and is certified via blockchain. Of course, there are challenges right now for such a system. First of all, it's the lack of standardization for materials in additive manufacturing, and the carbon accounting is for right now difficult because data is missing. And to get these data, collaboration of all stakeholders along the chain in the future is needed to get these data. But we see big benefits from there. First of all, naturally the regulatory compliance is a big topic. But the main reason why we are doing it, because we want to reduce waste. We want to have a higher resource efficiency for additive manufacturing, and overall to generate a smaller CO2 footprint by using more efficient secondary materials. So to sum it up, our big goal is to widen the possibilities of additive manufacturing via a wider material field for additive manufacturing. And we want to do it for your application and your material. Thank you.
Yeah, Stefan, thanks for the insightful presentation. Just to leave this slide on, if you look at the middle, the little cubes, that's actually the result of our parameter study we did by originating from original die casting material, which is used down
you can see on the left.
There's also the atomized powder on the left, the cubes after design of experiment. The final product is not yet there, but it looks very promising. And it's also in our exhibition next door that we will enter after the presentations, so you can touch the results firsthand. With that said, yeah, material is an extremely important piece in the whole additive manufacturing domain, enabling our applications at different customers. And also material handling is very important, so this is the point where I want to hand over to Martina, who is also not only talking about automation in additive manufacturing, but also about some innovative ways how to handle material during the process. So Martina, your stage. Take your time. Thanks again, Stefan.
So, yeah, good morning, everyone. I'm Martina RICCIO. First of all, I want to thank you, Matthias, for this opportunity. I work at Additive Industries, which is a laser powder bed fusion system manufacturer based in Eindhoven, so we are a Dutch company. And I guess now you are wondering why am I showing a Formula 1 car instead of a laser powder bed fusion system. So this is because who knows us also knows that we have a long-lasting partnership with the Alfa Romeo Formula 1 team, and we are very proud of it, also because you know that in the Formula 1 there is it's an high demanding industry in which the technology development is very fast. Every year they need to change their car, and they need to push the boundaries of every technology. I will later on tell you a bit more what are the results they achieved with our system. But then let's go to the topic of the presentation. So the role of the automation into the laser powder bed fusion. A couple of years ago, Forbes has published this study about the automation into the metal AM, finding which are the main benefits that were considered by the published on the automation with the additive manufacturing. So the weird thing is that everyone stated the lower labor cost as the first and main benefit, which is okay. Yeah, of course, automation means less manpower, but if you think about additive manufacturing, it's not the main voice of cost, the manual part. There are the machinery, the powder, and all other things. So, okay, that's true. There is less manpower, but this is not the main benefit. The main benefit of automation are the others, and the first one is the increased production output. Why? Because automating the process, you can avoid all the waiting times that are needed to wait for the operator to be there. So with the same number of machines, you can basically have a highest product throughput at the end of the process. The second good benefit is the more consistent and improved process. Again, if you reduce the number of manual operations, you reduce the less consistency on the process, because you know that the human being is not consistent by definition. There might be days in which it's very performing and days that maybe it's not giving the best. We are human, while the automation is not. So improved quality for that. Improved worker safety, this is another important one. In laser bed, powder bed fusion, when the process is not automated, the operators are exposed to the powder, which is not really good. By using automation, this can be avoided, and so that's another big benefit. And then the last one, maybe this is the less intuitive one, is the fact that by reducing the time that the people need to work on the system and on the process, then they will have more free time to focus on different things, and also, for example, to focus on improving the other part of the process, like, for example, post-processing. Sometimes we really focus on, let's improve the productivity, the laser productivity, and then we forget that maybe the part is waiting for the ARCIDIACONO for days because there is a bottleneck there. So, more focus on the high-level process. So, which are today what are the main pain points of the metal AM, which has been identified? This is very interesting. The AM Power report in 2023, so this year, has reported an utilization rate of the current worldwide installed base of laser powder bed fusion system as only 62%. Now, there are two reasons for that. One is that there are few companies which are very new in the market, and so the utilization rate is low because they are still finding the business case and the application, and okay, this is normal in the scaling up process. But the other point that's very important is the timing. And with timing, I mean that who is familiar with these technologies know that when we start a job, we don't know when it's finished, or we know, but we cannot really control it. It might finish during the night, and maybe we don't have a shift during the night. The operator is not there. So if a job finished during the night, the machine will stay in standby until the morning, and then that time goes into a sum of times that will lower your utilization rate. And here the automation will play a role. Another pain point is the powder handling, as I also mentioned before. It's still quite normal to see into metal AM production. The operators dressed up with this space-like suits because they need to prevent and to stay not exposed with the powder. Again, okay, this will prevent the exposure, but it's not really comfortable and convenient to work in this condition. Another pain point, calibration and diagnostic. Again, this is very important to have a consistent process. We need also to control the machine, the laser, the calibration. There are a couple of standard bodies like the AMS or the ASTM that are now finalizing and releasing more and more standards. The question is, how can we apply this standard in a consistent way? How we can be sure that this works? And the last pain point we see is the link between the printing process and the post-processing. The reason why there are screws there is because, again, if you are familiar with this process, you know that sometimes it's not very easy on, because you need an operator to unscrew the build plates from the machine, then move it to the next step, and maybe screw it again. This is not really something that can be easily automated. Now, in the next slide, I want to show you what are the possibilities that automation gives to the laser powder bed fusion, and in particular, how we in additive industries have implemented that. So the first part is adding about the utilization rate. It's adding robotics into the process, so the automation. For example, the build plate handling and the build plate leveling is done automatically, as well as having a robot in our machine that moves automatically the build plates from the process chamber up to the exchange chamber and all these kind of things. With this way, we don't need to wait for the operator to be back in the office or in the production floor during the morning. But in one of our fully configured machine, we can run up to 8 jobs in series in even different materials without any manual operation. So you can just press play and the machine will do everything automatically. The second point is the industrial hopper and the internal cycling, which answer the question about the powder. So as I said before, the powder exposure, the exposure of the operator with the powder is a big problem. And so for this, we try to avoid. We are avoiding it by adding this. You can see it here. It's called the PLT. It's powder loading tool. It's a tank which can be filled directly by the additive, by the powder manufacturer, and goes directly into the machine. So we have two benefits here. One is, of course, there is no exposure of powder and operator. The second one is also that the loading of the powder can be done automatically while the printer is printing, so there is no downtime for loading the powder. Calibration, software and hardware. So again, here we have developed different hardwares and software to calibrate the laser in an automated way. With this software in the picture, we see what we call the multi-beam tool. It's a tool which automatically calibrates all the laser with the laser power or also the laser beam shape and distribution. Automatically just pressing play. So we don't have the problem with the consistency that are common when the operator does this test. And also we don't have very long service time, because every customer can do it autonomously without even calling the OEM to do the calibration. And because everything is controlled by an algorithm, that's consistent. Open interface, this is regarding the linking to the post-processing. So from the beginning, the metal fab has been designed with this exchange model and with an unbolted build plates. So there are no screw, nothing, and this design is compatible with any production robot. So easily, when integrated into a autonomous or a very automated factory, then a robot can just go there, take the build plates with the part and move it to the heat treatment, to the wire EDM, and so on. So, which are then the values of the automation? The increased capacity, as I said, because with the same number of machines, you will have a highest throughput, because you don't have all the waiting time due to waiting the operators to be there. And I guess overall equipment effectiveness, highest OEE, because of the robustness of the process that has been improved with the automation. Then, as I said at the beginning, Alfa Romeo Formula One team is one of our partners, and I want to show you a few numbers regarding their production with Metal IM, and in particular with our metal fab. So they now have 4 metal fab on their production floor, with only half FTE working on that with a single shift. An available capacity above 95%, and a utilization rate above 90%, which, if we compare it with the average of the world that is 62, that's much better. Maybe these numbers are not very big for you in the automotive. In the Formula One, they are already big. But with our machine, last year they produced between 27,000 to 37,000 parts in a year, with half operator working on that. And with this, I finished my presentation. I thank you, and I will be happy to answer your question during the Q&A session. Thanks.
Thank you very much, Martina, for providing the insight on how different pieces in additive come now together to create a more autonomous and automated system. But only this is half of the story, because a printed part is not a finished part, and automation doesn't stop at printing. So I see Jan is already grinning hard. So yeah. Jan is now speaking about a bit in the automation domain of post-processing, because yeah, we have to always consider, as like in all other manufacturing processes, printing is not a standalone process. It's not a magic process where final parts drop out in the rarest cases. So we always need post-processing, we always need machining, the old dimension of machining. And how we get these two dimensions together, Jan will tell us now. So no one can describe it better than you, so your stage.
Thank you, Matthias, and thank you to all previous speakers. You've basically made my case within your presentations. I found it quite beautifully, pointing exactly that out. And I'm always glad to be at events that acknowledge that printed parts are not finished parts, because the reality is exactly that. This is not academia. Ideally, this will be production. So my name is Jan Bremer from BCT. We're a small family-owned company, and I'm head of R&D at the company. And I will speak about the automation of these process chains using what we call adaptive machining. So if you go high level enough, production is extremely simple. You have a specification and you want a part. And if you're the end customer, ideally, you really don't care how. So how we fill these lines are up to us all here. And realistically, there's multiple ways. And it's very important to remember that specification-driven manufacturing is the beginning of really becoming a good and sustainable production, because we've seen it in different cases also from the OEM themselves. This is the way to understand that there's not just one way. And traditionally, I think we all know, you just mill it from a billet, because very simply, just go for it. You just need one part. Who cares? You have a machine anyway. It's there. But there's many different ways to achieve this. And one thing is to remember, AM used to be at a level of maturity that this was never an option. Not really to ever really do automation, but we've seen now very impressive talks and insights how this is now an option. And the big question now remains really, is this now a drop-in? Because currently it's dominated by use cases we've seen that have brilliant advantages due to process-specific advantages. However, the complexity is still there. A lot of this is now automated, but still, it's not really the drop-in replacement many people seem to claim, because the one thing, like Matthias said, there's a bit of a pain point right at the end when the part looks really nice, but let's put the finger into the wound a bit. This is supposed to fit a gasket, and thank you again for allowing us to show the real study here. That's not really going to work. So we all know the specs on the surface aren't there, not fully to the spec that we need for technologically functional surface. We all also know here that subtractive will be necessary. And our job now is to bring the good old manufacturing method of subtractive into this new and great world. And we have a lot of challenges, and I think most of us here are fully aware of them. It's residual stresses, it's shape deviations, the positioning is a problem, because if you don't have any clear references on any part, good luck clamping that to spec. So in reality, we need to do a lot of things. And I'll do a little excursion into our wording we always use. One is, what is the best fit? And I think that's pretty good to understand. In the end, it's finding your part in the part. Didn't Michelangelo say, right, the statue is already there in the marble? We do the same, just in manufacturing. So we try to find for each and every part the right way to do this part. And the way we do it is we don't move the part around. And if there's people here who do post-machining conventionally in additive manufacturing, that's about the most horrible job I can imagine, putting new shims under every part every half an hour. And we see that a lot. And that's still the reality there is, but we try to do it the other way around. We'll just move the software and the digital side towards your part. We'll make it work. And there's actually a second level to this. This is what we call adaptive machining. Now we found the position, and we come, and at this point it makes sense to introduce what BCT does as a main business. We come from high-end automation and aerospace component overhaul. Meaning, there's another way to really ruin your fitting and your surface. It's flying the part for 12,000 hours. And the stuff we see going in doesn't look like the spec at all. And it is a necessary way to do it, to adapt to every individual part, because a part looks very different if it's flown through sand for 12 years or if it's flown in clear, crisp Nordic air, right? So this is where we come from, and this is why we have this toolkit available to do what I'm going to show you, that we can even warp the program itself onto each part. The study you'll see is actually just rigid body, but this goes a bit too deep for 10 minutes. So let's find a part, and let's find it with what we call machine integrated measuring and adaptive machining. And what we will do, and what I will show you now also in a quick video in a minute, is we'll do things that are currently simply impossible in the conventional chains. We need to find a part that has no reference, that has only freeform surfaces sometimes, so there's no clear coordinate system available. We'll do it by spanning individual specification-based coordinate systems, meaning this flange doesn't really care, because if there's a flexible tube to it, where the rest of the part is, this just needs to be right for the gasket and the fitting itself. So you can go really deep and complex in building these sorts of logics. And again, if necessary, especially in areas of support, we can basically drape the program onto the part to get this smooth and transition-free transfer between machined and unmachined, because the mechanical and corrosion implications of having a hard edge in the part can sometimes be very critical. And all of this, of course, in the spirit of today, is fully automated. And the beautiful thing again is we make the machine a measuring machine. So just to throw in a little gadget again, we can do quality assurance afterwards. So we will check every part afterwards as well. So enough of theory, let's look at it. That's our software running. You see on the left we build a process tree in the end that will be run. So we send the machine on its way. Let's find the part. And we'll find the part, we'll do the math, and we'll find that this part has the most homogeneous oversize as shown. And then we just simply move the program onto this very part and do it. And I'll leave you to a very meditative 30 seconds of finish milling of this part to enjoy. In case you didn't notice, this is sped up. So, quality assurance, and we get a green from the software. We got a very regular oversize, so we're happy with this. And you can actually see this physical part in the show later on. I've brought it with me, so we can also happily discuss the ins and outs of this problem later on. So, the overarching vision behind this is actually quite large, I think, as it is present here. It's a very positive vision. I actually found the last slide I loved in your presentation is the mobile production block. Is exactly that, because for us the future of production is resilient and agile. And that's a lot of big words everyone uses all day, but that has actually some very simple solutions as in putting them. For one, we need to definitely improve working conditions. Rightfully said, you don't really want to be around powder all day, right? So that's one way of doing it. But we also do it by bringing intelligence to the shop floor level. This software isn't running in the office. This software is running the machine. So it's next to the operator. It gives feedback to the operator and it allows intervention of the operator if needed or wanted. But that also makes the job more interesting. We improve the quality assurance of the whole thing by really collecting a lot more data. This software can add on features like monitoring milling forces, integrating laser line scanners. So we can do a whole lot more in data if you're willing to mine the data mine, right, realistically. And the flexibility in this is you can basically throw in whatever you want. And as long as there is a mathematical solution in the range that the software is permitted to do, you will get the same result. And that has really big implications in production. And again, the data-driven analysis becomes possible when you scale and you left the machine for 8 build jobs for a week, right? You might also be interested after leaving the milling machine alone for 2 days, what has happened. And you will have data on that. And really, you will see improvements all throughout. So in the end, ideally, when you get the next specification, it's not that you don't care, but you have the choice of throwing in maybe a casting, and then you do some adaptive laser cladding onto it to do hard facing locally, and then you finish it and you're done. Or you really feel like running your powder bed machine today, and you mill that adaptively, and you're done. Or, and here comes the sustainable part, again, that is our core business, maybe you have an old part, which you then prepare by milling, weld on something to fix it, and then you're done. So this freedom of choice is what we try to give with what we call adaptive processes, and I'm really looking forward to seeing this kind of operation here. Thank you very much.
Thank you, Jan. I fear that closes all the enabler sessions, and now I have to deliver. But yeah, as promised, I come last to wrap it all up a bit and tell you now deeper what we are building here with all these inputs that we get from our customers, potential customers, and from all the hardware and software that's evolving on the market. And I would say our goal is to achieve somewhat called unparalleled productivity in AM through strict focus and integration. That would sum it all up. So yeah, for those who might have joined a bit later, I'm Matthias Wiese, CEO of ADDITIVE here. Had a long story in the automotive domain before joining the little team here, and now we are pushing the limits of aluminum additive manufacturing. So I just want to build an agenda to answer 3 questions to you. So the most important, that's the label of the event today, Meet ADDITIVE. So most important question probably is, who are we? Yeah? But a question or 2 questions that also underline what we are why do many firms in our domain struggle to use AM in a productive way, and what allows us in particular to perform better in this domain. So let's jump right in. I think in the very beginning Harald already addressed this topic, but I also will keep it short, but for those who might join later online. We are ADDITIVE. We were established in 2020 out of a startup incubator here in the Technikon Group. We are now a team of 6 experts and yeah, basically growing. 6 experts that came from all the neighboring sister companies to work on this mission to becoming a flexible volume manufacturer of additively manufactured aluminum components, yeah, for the domains of machine engineering and automotive. So yeah, just very quickly, the 2 big sisters we are heavily learning from is Durst. Harald already addressed that. 800 employees, quarter billion of revenue, specialized in digital printing all around the globe, and actually also spun out of Durst earlier Alupress, which is now yeah, tier supplier for highly complex casting components in the automotive domains. What is really interesting about all these different companies is what they are bringing together. Yeah? On the left side we see some components that are usually situated in the Durst printer, so very intricate, complex structures that are milled from billet with internal routings of fluids in the digital printers. And on the right side, very complex castings, the pure mass manufacturing, the millions, not the hundreds. And we see that both these domains benefit a lot from additive manufacturing. So just to take an example, which was published before for our customers, Techno have been realized injector valve bodies for their new snow cannons. They're also here on site today. You can speak to them. And also the part will be on display in the exhibition later. So we are combining more than half of a century in know-how of metal precision components here in our little company right now, with a new production method which is called AM, obviously. But let's dive a little bit deeper into why so many firms struggle to use AM productively. And that basically starts at understanding the customer needs and the customer wants, right? So we heard from Schaeffler, we heard from Alupress, also we heard from Technoalpine. There might be a case for fast functional prototypes to test my product, go to market. There might be a need for small series because it's a low runner, or we need to supply some parts in the aftermarket. We can use the technology as a supply chain backup. That's a bit far off from the timestamp now, because it needs to be done for flexible factories that are distributed around the world. And the last domain is definitely the AM-only design parts, so parts that just can be realized by this particular technology, but this is really slowly evolving in the industry, so that's not the main case. If you look at the ones, obviously AM comes to the customers to use the technology intrinsic flexibility, right? To leverage the short lead times, the process promises, and obviously also by using that, still maintaining the usual quality level. That's so far so nice. Then two factors come into play which are a bit more stressful for producing companies like us, and that's cost and impact, right? So obviously we want to achieve everything at reasonable cost. AM per se, we heard it from Francesco already, is a lot more costly than mass manufacturing technologies. But we see also a very good potential to reduce the impact of actions of companies, because we are really more material efficient when it comes to the final part. So all of these, nice goals, but they're often not universally achievable together. We also addressed it a bit through the different presentations. IAM doesn't come as a single process. We have a complete process chain from printing to quality, over depowdering, material treatments like heat treatment, removing the supports, and machining, as we heard in the last presentation. So there's a lot of flows of information, material wastes, and obviously also products along the process chain. That comes with a lot of challenges, right? So as a producer or a production company, we want to achieve high uptimes for our equipment. Yeah, we want to maintain a low lead time for the customer, so he gets he or she gets his products fast and on time. We need to coordinate all the processes that are in the process chain to achieve these, and also assure at least the base level of quality the customer expects. But we also not only have challenges, we have real problems. Yeah, the real problem here is with AM there's a high amount of manual data preparation involved. Yeah, there's a labor-intense process, labor-intense interfaces. Martina already addressed that. You have to transfer materials, you have to transfer build plates between machines, between processing steps, and also we addressed this. Martina, I think you also already said that the quality from the product is extremely coupled to the operator. So if a person drops out of your company the next week, it's not guaranteed that you can manufacture the product at the same quality level, especially in AM. So what we see in the market right now is this typical application-centric approach, right? AM is basically fired at everything that looks like it's printable. That means we are opening up not only on the aluminum process chain, we are also using, for example, copper. We could use, basically steel. We could use titanium to pick all these low-hanging fruits and get all these applications into the business. What happens with the underlying manufacturing system is it inflates. Yeah, so there's really the printers are coupled to the material usually. So you cannot change between materials without high efforts, and this means dropping OEEs. Also, everything that comes in contact with powder has the risk of contamination. Yeah? So depowdering needs dedicated machines. Treatments, more or less desupporting. If you desupport aluminum, you can saw it from the build plate. If you desupport very hard steel alloy, you might need to wire erode it from the build platform, so you need another machine. And obviously also in the machining step, it inflates the amount of tools that it's needed. So we see the inflation of manufacturing system. We see problems in load shifting and maintaining a high OEE. We see that the automation potential with this inflating manufacturing system is limited because I have so many interfaces. And as a producer, I more accumulate general knowledge for all the processes and all the domains rather than specialized knowledge across one particular process chain in one material domain. So, wrapping it up, this is why we focus on aluminium. So, we heard from 3 enablers today, and I want to pick it up one by one. So, with Materia, we are looking down this pipeline of tailored aluminum alloys, to enable our customers with different alloys that are more tailored to their application needs, and not only the standard aluminium you see in the market, LC10MG. We want to enhance the material recycling and circularity, and this is enabled by staying contamination free, staying with one material domain that you can actually, in the worst case, recycle it all together, and then go to basically reproduce material from there. And by just focusing on aluminum, we also get the deeper understanding of the parameter and material interaction, parameter material machine interaction, if we would be very clear here. The next stage is the print automation. Milling has been there for quite a while now. It's highly automated, but we just see this development happening in the printing domain, and that is where we take the inputs that are delivered by additive industries for having a higher productivity, autonomy, and material efficiency here. And also the very mission critical factor to decouple the operator from the overall quality of the print and the final product. And also we have the opportunity to integrate here, because the machine offers in-machine depowdering, so I'm getting rid of another process in the process chain and make a more lean process chain. And last but not least, as presented by Jan, adaptive machining. All the challenges that were very AM specific right now can now be mitigated by software solutions. We see that we have a higher throughput, less labor. We don't need to orient the part for hours in the machine to make sure every surface is touched that needs to be touched. It's automated, and we can in machine again integrate the final quality assessment, and when the part comes out from the machine, we are sure it fits and goes into outbound logistics and fulfills the wishes of our customer. So, just getting back to the whole Technikon ecosystem, what we also present here is kind of an extended value proposition in the product lifecycle. So, in the very beginning, you might remember CARMEN showing you the aluminum die casting product lifecycle. We are not just focusing on die casting to say that, but it's a big domain where we see a lot of applications happening with all these inputs we gathered from software and hardware. So, if you want to go to mass production, you can start your journey here with ADDAM for the first 100 parts. If you want the following millions, you head into a die casting process. And back again for the last 1,000 in aftermarket. But to be understanding this, it needs to be understood that you need to enable the AM process at the very birth of the product. It's very hard to do that after the product has been released and then going back from the aftermarket to try to specify all the requirements and get an AM aftermarket product when the product is already in series with a mass manufacturing technology and was not in parallel also enabled for AM. We will also be on Eurogus, just to say that, next January, displaying that with Alupress. So people here and people in the stream, feel free to visit us. We have a couple of use cases to tell to close this aluminum product lifecycle. So maybe, this answered one or two of the questions already. So who are we? We are ADDAM. We are your specialist for aluminum AM. And why do many firms in our domain struggle to utilize that in a productive way? As I said, there's usually not enough focus and sparse integration happening. It's more evolving from the lab. And last but not least, what allows us to perform better, we really focus on one material domain, and we strive for high integration of processes. So keep the process chain short and keep it small and narrow right from the start, and that's where we're going. So just to wrap it all up, the mission not only starts by printing at our facility. We heard it from Francesco. He said many OEMs, many tier ones have printers on site. They realize first prototypes, but when it then gets into B samples, where we go into hundreds, for example, it's also just not cost efficient to print it in-house often. So you might shift all that to a specialized production company, for example us, who is able to manufacture a couple of hundreds of these parts. And so we see that there might be also the need to educate operators how to look into more automated, more streamlined AM. So we are launching the ADDAM Academy to basically train operators here, certified by the DVS in Q1 2024. And we are able to educate along the complete process chain of aluminium. With that said, also from my side, thanks for your attention. It has been 75 minutes now. I would say we quickly build up the expert panel here. For the people in the stream, the screen will probably turn green for a second, but we will be back in a couple of minutes, and then all the experts that we're presenting are ready to take your questions. Thank you very much for joining us here. I think we are ready, right? Thanks for presenting here with us and underlining all the little pieces that are needed on the mission to take AM to the next level here. I just turn to the audience, so maybe to give you the space to ask some questions after listening to us for 75 minutes. Is there a question from the audience? Well, this is disturbingly quiet. One question. Yes, you maybe it would be worthwhile if you would introduce yourself very quickly so everybody gets know what
Yeah,
what's
sure.
happening.
Hey everyone, my name is David Nguyen. I'm a technical service engineer for Onshape, a PTC company which offers a cloud-native product development and integrated PDM solution. Thanks, thanks for this great event. It was great. I really enjoyed it. I always ask a lot of questions, so I don't want to take too much time. Sorry, I forgot the names now. From Jens, or what was your name, from Materia?
Stefan.
Stefan, sorry about that. Yes, I was wondering, do you actually develop your own machines as well? Because as a part of your of the process control, to produce your own powders.
We produce our own powders, but we don't produce our own machines yet, I have to say. There are some difficulties or some shortcomings with each and every system, so our goal is to overcome these shortcomings for us, that we can use it in the best possible way. But for right now, we are stuck with the machine we have. It's the most or the best machine as you can buy right now for these works that we do, and that's why we chose it. So it's a yes and no. So.
Okay, great. Thanks a lot. Can I go ahead straight away with a follow-up question for someone else? No, I go. Yeah.
Okay. It's your stage.
Yeah. Thanks. Then BCT, right? I was wondering, so the post-processing that we saw before, I mean, without, not to talk bad about it, but I mean, it looked like a quite straightforward part geometry, say, like it was a nice parametrically designed part, straight machining, it looked fairly straight in the fixture. And so I was wondering, then maybe it was just a 2.5 axis operation. How is it working? Can you do more complex geometries if there's a freeform part just kind of like somewhere randomly a bit oriented? Are you able to then accurately measure that part as well and do some more complex machining operations, 5-axis machining operations, some undercuts? Is that possible as well?
Yes, we're simply limited by mathematics, and they're quite powerful. So absolutely, the part, sadly, as you will see, will also be censored a bit by a plastics casing, so it will only show the area you've seen. And the biggest challenge being in aerospace as the main market is I can't show you the cool stuff. So the short answer is absolutely yes.
Okay, great, thanks.
Hi there. Muss ich drücken? Hi there, Peter Leibengut, Neutech Park Bolzano. Just a follow-up question to the machining. We are seeing these beautiful images from outward machining, but if I'm thinking about, let's say, heat exchange components where we do have inward shapes, which also need some kind of processing, are there some thoughts from your side on how to tackle that?
Well, in the end, the accessibility limits it. So there's a lot of sensorics options, there's a lot of thin touch probes, but if it's an enclosed space, it's not our space to work in. So very simply, for especially inside of flow hardware, the flow finishing methods are exactly suited for that, for a good reason, right? Because it will follow the liquid that will later run through. There's absolutely no point in doing that with machining. So I think we need to be very clear here. The goal of running a high precision CNC machine is to get a high precision, geometrically well-defined surface. Anything that is just flow, don't take the just wrong, right? In the sense that it's mainly a surface condition problem, for example corrosion also. There's a lot more potential in electrochemical finishing, in flow finishing. That's not the world of machining, absolutely not.
Thanks so far.
Hi, I'm Andreas OBERRAUCH from Skyward Experimental Rocketry from Politecnico di Milano, and I would have a question about the mechanical properties of the additive manufacturing. So we saw that we got a lot of benefits actually from using this process, as far as we saw like the maximum strain that the material can take. What's the effect on fatigue life, and how does the additive manufacturing affect the fatigue of a material, and is it consistent in the production?
I think I'm not the young person to answer that. Yeah.
I will take that question. It's a good point. I mean, I marked some stuff in the data table that I showed in dark green. That means properties are much better. In die casting, if we compare it, we have usually porosity. That is natural to the process. So we have there, let's say, a less good performance than when I take an AM sample, because it's much more dense. But if you talk about such an issues, for example, just relating to additive manufacturing, if I have, for example, the powder, and the powder is contaminated with the air, I have some oxidation, and I do some building, laser welding, whatever I do with it, I will see it in the component in the end, because it will blow up in some bubbles. You will have also porosity, only because of the storage is not perfect, yeah, because the system is not encapsulated. And then you have, of course, porosity, and porosity, each pore gives you cyclic fatigue that is reduced. So it depends on which processes you compare, but also within the AM process there are lots of influence factors. For example, also surface, yeah, if the roughness is in some notch too sharp, yeah, and you have a high roughness, you should use like electropolishing or some approaches to smoothen the surface, to reduce the risk.
Thanks a lot.
Okay, you're welcome.
Hello, my name is Christian from a company Mikado. Within the last few years, we have seen in the automotive industry some aluminium parts are growing tremendously under the keyword mega castings, and so now many companies are moving towards bigger parts. But we have seen that prototyping is extremely difficult on big parts. Is this a field where additive manufacturing could be good at extremely big aluminium parts, or is this something which is on the extreme opposite of low-hanging fruits?
Okay. Yeah, well, sure. So what do I think? From one point of view, yeah, as you said, the prototyping is the first part of the additive manufacturing. But what we are doing, why we were born, is actually to have a system, a platform that is able to run the serial production. I think that today we are already very nearby there. It's already the present is serial production. The thing is just to find the right application. When you find the right application and you have the right system, then you can go there. Yeah, maybe.
Yeah, what we also see from screening the market from the producer's perspective is we see that the systems are getting bigger and bigger. Yeah? The problem is yeah, you cannot betray physics after all. Yeah, so as the build volume grows, there is a lot of temperature gradients within the building chamber. You have to coordinate a lot of more lasers. Yeah, there are machines. I think the last one that was presented was a 16 laser machine in some Chinese manufacturer. In theory, yeah, that makes everything possible, but you always also have to consider to fill up such a machine with material. You have to invest a couple of 10,000s of euros in material. And if this build job interrupts, you're sitting on the cost. So it's also adding a high risk. In theory, so it's possible, it's already done. If it's, how to say, if it's a senseful application, I would highly doubt. Especially in the casting domains, you would be probably better off with sand casting and stuff like that. There are some parts in the aerospace industry, for example, we always see rocket engines or something like that that grow really tall, up to 1.5 meters, that are really special applications. Yeah? And I would say, from my knowledge, the market is also very small. Yeah? Or I don't know how many rocket manufacturers you know around the world, but there are not so many. So I think the most concerning issue is still automation in a reasonable size. And we don't want to compete with processes that are much more able to, how to say, realize big parts just from the better physical standpoint of realizing it, right? Casting is the way to go for big parts. Anything else? Okay, maybe I find a question from me towards the panel. From the perspective of production, we always think about what is necessary to enable our customers a bit more. I peeked into that with offering the training program we have, but maybe also addressing all of you, because you have certainly spoken to a lot of different customers. You have entered different industries as a machine provider, as material specialist, or being an OEM yourself. What's the main point to adopt the technology? Is it a matter of training? Is it a matter of knowledge accessibility? Is it a matter of, how to say, distrust in the material properties? What is your take on that? Maybe quick.
I think regarding the material cycle, what I was talking about before, it's the collaboration that is needed to establish such a cycle that is the biggest challenge for us right now. You have to get each and every stakeholder along the chain to collect and also send out data to keep track of the material. So for us, for enabling material cycle, the collaboration is the biggest step right now.
Yeah, from my side, I think the training and the knowledge is the basic, because at the moment what I see is that some companies and additive manufacturing in general is challenging to find the right application. So additive manufacturing makes sense when you find the right application. It started like, oh, with additive we can do whatever we can because it's freeform and etc. But that's not the right way of thinking. It's just finding the application, which might be maybe a simple part, but it's just maybe a consolidated part. So you reduce an assembly to a smaller part, and then you get the benefit of the additive. So the basic is having people trained in additive manufacturing, in design for additive, and find the right application for me. Yeah.
So, my perspective, my 2 pence is on this one. The blocking point for us so far was very openly cost, but now we found somehow some appealing use cases. So what's next? What I expect that is key for success are going to be 2 points. First of all, collaboration, as you said, between the different partners, and then integration. We have, as you said, Matthias, and I totally agree with you on this one, we have, if we want to use additive manufacturing successfully within our product life cycle, we have some spots of interest, but then we have also to start designing the parts since the beginning with additive in mind. We also have to integrate the material choice starting from the beginning. So again, integration and collaboration with the additive manufacturing partners is going to be key, I think, in the future.
Yeah, from a perspective of a die caster, yeah, it costs mainly because we are usually cost-driven, and to give us the flexibility at the early stages to react fast to the requests of our customers, and this is actually why we're using it already. On the other hand, I see already the approaches here, and I think exactly these points, the post-processing and the automation, is that what makes it even more successful. And if I might add my opinion as a material scientist, it is, as you said, the right process for the right application. So I think it's exactly what you said. It makes no sense to make 2 big parts if there is another better process.
Yeah, brilliant points, and I think mine is kind of at the interface of each of them. In the end, we all need to remember innovation is made by minds which are human. And as much as we always talk about automation, we can only automate away dull processes ideally to make the life better for everyone here. And I think it's still to a level education mission, because the design needs to be made from the first day on to be manufacturing flexible. And one of these manufacturing processes, which is now being alleviated to a level of automation and cost that makes it acceptable for most people, because in the end the customer just accepts it then on their part, is now additive. And I think we need to realize is we're in a very, very large space of a lot of options. So what we are all doing, and I think we're doing quite successfully, is that we're now pulling additive up to a level that it's competitive at all levels, and so its advantages can be leveraged with the buying department still approving. Because I think a lot of us come from academia, right? We enjoy the technology, but now we need to bring it literally to the masses, let the design engineers realize what is the potential, and give them quick and affordable access to getting the first parts into their company that let them prove the advantage.
Yeah, maybe I take the opportunity to thank you again also for the little expert session now, and looking at the time, we are 5 minutes over. That hurts my German heart. But yeah, with that said, I would close the stream from our side. So I'm inviting you all physically here to join us over to our shop floor in Kraftwerk, passing through Durst. So please stick together. Just a small announcement, no photos in the Durst building. Over in Kraftwerk, you can do whatever you want, nearly. For all the people that are still in the stream, if you have any questions left, as said, note them down, send us an email. We are happy to connect everyone who was participating today to present some more insights on additive manufacturing. Thank you very much from Brixen, and see you soon.